Then that goes into something called a system. We draw a system as a block diagram. That can be an amplifier. It can be some kind of thermochemical process. It can be anything. You don't care. The only thing we do is show a black box. And this thing has something called an H of T function that really is something you're going to get, we'll get into next lecture, but it's something that will define the output. You don't have to worry about that yet. The output is almost always defined as Y of T. Now Y of T is defined not as H of T times X of T, but as X of T convolved with H of T. You don't know what convolution is yet. The symbol for convolution is an asterisk. I will get to this next time. I need to put it up there now so I can reference what I'm talking about, all right? Just remember this. Everything's basic in block diagram. Input could be anything. Pressure, voltage, current, temperature, some input that's measurable and observable. And by the way, it could be digital or it could be analog. This is something we'll get to. It has to do with how the system operates on this to get the output here, Y of T. And I'll get to that later. Are you ready? All right. So this is just some basic laying the foundation stuff. Now the second thing I do is define the types of things we talk about with X of T in terms of what they can be. Well, X of T can be continuous time. X of T can be continuous time and have all possible values, something like this. All right? The only thing I'm showing you there is something that can have any possible values, but it's continuous. There aren't only states that are discrete or quantized. They can have any value, and here, time is continuous. Now, the best thing you can think about there is think about the output voltage from like a microphone. It's continuous, right, versus time, if you actually had something that was reading versus time, and there's no discrete levels. The next type of thing that can happen is where you have, and you don't have to label this, don't worry about this, I'm just giving some reference. The next is when you have something where you're going to have X of T here, and this is continuous time, but now the levels are discrete. Something like this. They can only be, say, 1, 2, 3, 4, 5. Get it? So the output values, or the input values, X of T has only certain values that are allowable. It could be 0, it could be 1, 2, and so forth. This is something that is taking you towards digital stuff. It's quantizing things. Now, you can imagine if we tried to take this signal and say we had 20 levels from the maximum to the minimum value, then we partition that region up. If we tried to make each one of these points something like that, we would get error. We would get what's called quantization error. Does that make sense to everybody? All right. But that's the way we're going, in that direction. Now that's continuous time, discrete values of the signal. Sometimes it's referred to digital. That's really not a good way to do it, and the reason is this. Digital almost always implies 1, 0, 1, 0. It implies only two possible values. Now, frankly, a digital number, like an 8-bit number right there, is 2 to the 8 values, right? But technically speaking, if you use the word digital and showing something like that, it usually means zeros or ones. But don't worry about that. We'll get to that later. How many of software, you got an emphasis in wireless here? Software engineering? All right, you'll find out that this is real important. Now, after that, now you go where you get discrete time. Now in the time domain, you got 0, 1, 2, 3, 4, 5, and so forth. But now here, X of T can only have values at the actual points that are integer values. They can have any possible values. All right, these can be any possible values, but they're only measured at discrete points in time. This is just giving you some reference here. That should make sense to you, right? Now we basically said, I've taken that signal over here, and I've simply sampled it at given points in time, and it's up here, right? And then finally, the last thing that happens, and you might guess, is going to be discrete values of X and at discrete times. And that's really what we're going to end up at, where now we label this really as X of N here, where N is going to be the integer. And this will be 0, 1, 2, 3, 4, and so forth. And now you're going to have only discrete values. Say, I'm going to use 3. Say there, here, 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 and back here. It can only have discrete values. Follow me? That's the closest thing to digital. I mean, to where we have discrete time, discrete values of the signal, discrete points in time. And that's something we're going to work towards with all our signal processing we do in this course. And eventually, if time allows, we'll get into actually taking that into a digital, well, you're going to get that. I don't think you get it in digital electronics, you might, but you're going to get it in a lot of your other courses. How to do, take an A to D converter, for instance, analog to digital conversion. All right. Now, next thing, this is just bringing you up to speed on things you need to know. Next thing is interesting. Now we're going to introduce you to a whole bunch of different concepts you've never had before. I think about the best way to do this, and there is no best way. If you have a question, you can ask it in class. You don't have to worry about raising your hand unless, I mean, if you're too disruptive, I'll quiet you down. But generally speaking, most people kind of understand what's going on. All right, now, now we're going to talk about some properties before we do the functions. So let's say I give you a function like this. Here's where you start paying attention. Take good notes. I'm going to say I have a function that looks like this in time. I'm going to have an x of t that looks like this. It goes from 0 to 1, and it hits the value of 1 here, and then it goes back to 0 again. And that's the function. Don't worry about how to mathematically define it. So now the next thing I need to do is find out what it looks like when there's a shift involved, either to the left or to the right. Let me ask you before back. Can you all see this back there? If you cannot see it, if it's too small, yell. Just yell it. All right. What happens now if you were asked to draw this function? I think you get these on your ACT exams and SAT. Suppose I have x of t minus 1. Now, what does that look like? Think for a second. This is 0. Well, the way you go about doing this reasoning through yourself is this. Where did this function turn on? At t equals 0. So when the argument here is 0 is where it turns on, right? When is this argument 0? T minus 1 is 0. T is 1. Turns on at 1. Now, where is this function? Actually, that's all you need to know. Where is this function a maximum? At 1. Or when the argument is 1. When is the argument 1 here?
2.
T minus 1 is 1, and t is 2, right? And you get the idea. What I've just shown you is something that is simply a shift, and this is a right shift. It's a shift to my right. Do you follow me in that? I'm going to see this right here. It's a simple principle, but it's very important to understand. Now, the next thing, and I'm going to use the same drawing. And I bet you everybody gets this. Next thing I'm going to do, still use this x of t. What does x of t plus 1 look like? How do you figure it out, guys? Where does the function turn on, the original one? T equals
0.
What happens there? T plus 1 is 0, or t equals minus 1, right? So this one shifts everything this way, right? And that's not the scale, but you get the idea, right, class? All right, now that's a left shift and a right shift. Very important. It seems trivial. Trust me, it's not. And I speak from experience, teaching people this stuff. Now what happens when I do this? I want you to think about this. What if I make this argument not t, but minus t? Now what happens? Ask yourself the logical questions. Where did this function start here? T equals, where does it stop? 2, right? So minus t would be equal to 0, or t would be 0, correct, class? So we know it starts right here. But it stops when the argument is 2, right? That means minus t is 2, or t is minus 2, right? So it looks like this. Please watch me on this. This gets a little strange quick. Are you with me on this, class? How many see this concept? Now, don't feel you understand it if you, oh yeah, I see what you mean. You work these problems I give you tonight. Is that these are, you think they're a gimme, they're not. I mean, bet your friends on who gets the right answer, and don't show the answers and see what happens. You'll be surprised at how many times you get confused in this. It's like playing chess the first time when you move into some competition at the like 1600, 1700 level. All of a sudden you realize how much does anybody ever play chess, by the way? I hope I'm talking to people enough. If you've ever played on, you'll understand when all of a sudden you're in over your head and you think you weren't. Right? It happens to me all the time. I had a Federation master who was a student of mine. I'll tell you this. This is actually kind of fun. All right, so this guy is ex-military. He's an African-American student. His name's Stephen Muhammad. You can look it up. Stephen Muhammad. Brilliant guy. Didn't know he was a chess player. Had no idea he was a chess player. He's upstairs asking me some EMAG questions. Another grad student in my office named Dan Fairclough, who now runs a private company, is worth a fortune. He runs Iris. He's one of the 3 owners. Comes up there. We're doing some work, fairly sophisticated, graduate level work related to journal publications and stuff like this. He comes in and wants a few questions. I'm there, all right, have a seat, I'll get to you. I had a chess game. Does anybody know what chess master is? It's a chess game, right, at the highest level, the grandmaster level. So he says, do you play chess? Now this kid's in my class. This is the kind of kids I get in my class. Super bright kids. He goes, yeah. I said, yeah, I play a little. I'm not good. Well, we should play sometime with that. All right, we'll play. So I'm talking, what's your question? He asked me any of my questions. He goes, you mind if I play? Have at it. It's on the highest level. Nobody beats this thing. So he starts playing, he's talking, and I'm looking after about 10 moves. He's got an advantage. Look at this guy. This is weird. He ends up beating Machine. So now who are you? I figured they sent in some guy just to spook me. Turns out he was at that time a Federation master. He's now, I believe, an international master. He'll probably be a grandmaster unless he gives lessons. And I am so glad I didn't play him for money. Anyway, that's the kind of guys I get in my class. Because if you're good at chess and reasoning, you're good at this. And if you're not, you're probably not good at this. And that's his words, not mine. Anyway, are you with me on this so far? All right, now the next thing is what happens if it's not this, but if the argument is, say, capital T, not capital T, let me just put it as 1 minus T. Now what does that look like? Think about it. How did I determine the other place? What happens there? Well, think again. I'm going to erase this one. That was just minus T, right? What does the 1 do? Well, 1 minus T equals 0, right? Or T equals 1, right? Now, where is it at a peak? At 1, right? 1 minus T equals 1, right? Or T equals 0, right? And what have I just done? I've taken the original here that was minus T and I'm shifting it to the right. Am I not, class? As a matter of fact, how many see this right here? Y'all see it? Right? Can you all see it back there, guys? You follow me what I'm doing? I'm trying to show you with numbers, but let me just show you the general trend. When you get x of minus t as such, and that's this, it just takes literally this and flips it to the other side. Just if you could swing that on an axis, on the actual vertical axis, it puts it over here. Then when you add a number here, any number t, what it actually does is now take the whole function and then move it so that this point is at t. Do you follow me, class? This will become very important in some of the stuff we'll do later. How many see this right here? All right, I'm going to give you problems like this, but this is a shift, right? But it's a shift with a negative argument for your actual horizontal coordinate. Understand, everyone? I know you may not like it, but you'll see that this becomes very, very important to understand that. All right, next. Did anybody look up Stephen Muhammad, by the way? I was talking? No? amazed at this. He was sitting in my class. He's a very bright guy. He's a smart kid. He'll do okay. I didn't realize I had Einstein there. But the next thing I want to talk about is some of the functions that we're dealing with. Here's the first function that you've never seen before. It's called a delta function, or a Dirac delta function, or an impulse function. The symbol is delta t. It's called a delta function. It's called an impulse function. And sometimes a Dirac delta. All right, doesn't matter what you call it. Let me tell you something about delta t. What it is this. I always do it this way. If this is x of t here, and this is t, or let me call it delta t. If this is delta t, here's how it's defined, the easy way. If this is delta t, the height of this is 1 over delta t, and the function is defined in the limit as delta t approaches 0, all right? So what this thing is becoming is a needle. The way it's usually represented is this. It's something, the delta t looks like this versus t. It's infinitely tall and infinitesimally wide. But there's one simple fact about this that some of you realize. What is the area under that curve? 1. And that's the important thing to understand. With a delta function, it turns on where the argument in here is 0. It has an infinite height theoretically, but it has an infinitesimally small width. Right? That's called a delta function. From this function, we get a whole host of other functions by integration and differentiation. Right now, integration. The next function is u of t. Now that is something that they call it a switching function. Really, u of t is something that is defined as the integral from minus infinity to t of delta of t prime dt prime. The reason I prime that t there is because it's inside the kernel of integration. It's inside the integral. And your argument here cannot be the same as that. This is called the dummy variable. It goes away. Now, if you look at that, if you look at this right here, what is this really? Think about it. What if t is less than 0? Really, what I've got here is, delta t, if this is versus t, this is 0. What's the value of delta t down here? 0. It's 0, right? What's the value of delta t up here? 0, right? The only place it's defined is when the argument t is 0, right? But if you integrate that function, if this is greater than 0, then u of t is 1, isn't it? Because the area under there is 1. And if it's less than that, it's 0. As a matter of fact, u of t is defined as 1 for t equal to or greater than 0, and it's defined as 0 for t less than 0. So u of t looks like this. It just comes there, and then bang, it's at 1, and it stays there. Follow me on this, class? That's u of t. I'm going to get through the functions and go through some. I've got a few more functions. Are you with me so far? Has anybody seen the Dirac delta function or u of t before in here? You have? In what class? You saw u of t and delta t in your diffie Q? I'm glad to see that. All right, a lot of people know. Yeah.
Can you explain why the delta equals 1?
Well, when you're integrating a function, if you look at this, just think about this. You're integrating through, you get the area, right? Just take width times height. 1 over t times 1 over delta t times delta t is 1. That's the reason. The area is 1. There's different ways to define it. Some people find they write a Gaussian functional form that take the limit as the actual standard deviation goes to 0. There's different ways. It's the same thing. It's just taking everything and crushing it down to a needle. It's infinitely tall, but infinitesimally small, but width, infinitesimally narrow. Now, for this one right here, this is a really useful function because if you look at that, wherever the argument is 0, that's when it goes from 0 to 1, right? You see we can model a switch very easily with that, couldn't we? If we put u of t next to a source of 10 volts, then that would be 0 until what? T was greater than 0, then it would go to 10 volts. Wouldn't it, class? Does that make sense? I'll get to that later. But this is a real useful function. Next function is called a ramp function. This is r of t. And the ramp function is simply the integral from minus infinity to t of u of t prime dt prime. Well, if you think about that, now I'm going to integrate this function, correct, class? I'm integrating the area under the curve. It's going to be 0 until what? T equals 0, correct? If you look at the ramp function, really the way it's going to look like is this. I'll draw it, then I'll write down the actual value. R of t will be 0. If I'm talking about the integral from minus infinity to t of this function. Well, if I'm integrating from minus infinity, there's 0, I mean 0, 0, 0, then I go from here to 1, right? Then I have what? If I'm greater than 0, it would be what? 1 times t would be the area under there, correct, class? As a matter of fact, the ramp function does this. It goes here, and then it goes like this, where the slope of this is 1 to 1, and this is simply t times u of t is another way to define it. T times u of t. Do you follow me on that, class? T is just a straight line, right? U of t turns it on at 0. That's another way to define it. Follow me, class? You gotta be careful with this one now and that one, because I'll tell you why. What people do oftentimes is forget the u of t and they say it's just t. Well, t goes on like this, doesn't it? Follow me? But this ramp function doesn't. That's an important fact. All right? So that's the ramp function. We can take it a step further. There's no need to. If we integrate the ramp function, what do we get? Well, if we integrate this that looks like t u of t, we get t squared over 2 u of t. Wouldn't we, class? Follow me in that? We could keep going down that road, but it's not unnecessary. These are the basic functions right here we need to talk about. There's a few others I'm going to put in that we need to get down before we continue. All right. The next function is called a pulse function. Or the rect function. Now I'm going to tell you this. Either one is the same thing. I like the pulse. The symbol for the pulse function is just a p with a subscript tau, and the argument is t. It's the same thing as this, a rect function with an argument of t divided by tau. They're both the same, and I'm going to draw them. And what it defines is this. Either the pulse function of t or the rect function of t over tau is simply this. It's something that has a width of tau and a height of 1. Are you with me? Has anybody seen these functions at all? No? Well, they're useful, and you can actually build this function very easily out of a couple of u of t functions. Believe it or not, very easily. And I'll do it in a second, but take a look at that. That's a pulse function, right? So really it's something that's on and then off. It's going to have a certain length that the pulse is turned on at, and it's used all the time. Now let me show you something about this. If we wanted to build that from a u of t, say I wanted to construct that, but not use the symbol pulse, I wanted to use u of t for whatever reason. Then I could say, well, the pulse function, p tau of t, or the rect, well, it turns on at minus tau over 2, correct? So we could use a u of t, right? But we don't want it to turn on at 0, we want it to turn on at t over, or tau over 2, correct? So what do we add to it, or subtract from it? Tau over 2, right? If we add plus tau over 2, now what does that do? Well, that u of t turns on, goes to 1, right? All see that in the back, guys? And it stays there until when? So how do we shut it off? Any ideas? Subtract a u of t, right. Subtract a u of t, help me? Minus tau over 2, right? How many see that? Now that's how we built a pulse based on u of t's. Some of you people will be programming software, and with all these, especially when you get into the real basic languages, you have only a certain set of functions you can use, and you have to build all your others. And this is trying to give you a heads up on some of the ways to think about these things. All right, that's a pulse function. That's used all the time. Let me ask you a question, too, while I'm at it. What does this look like? If I had a pulse function of 4 of t minus 2, I'm going to go through this how you figure it out. So what does that look like? Count it. Think about it for a second. Well, what is this function right here? I'm using the symbol pulse. The tau is what? The width, right? Isn't it? This total span here is tau. So I know it's 4. I know it's got a width of 4. But that doesn't tell me everything. What else do I need? I need to know where it's centered, right? Where is it centered? Where the argument t is 0. When is this 0? T equals 2. So I know it's centered at 2, right here, and it's got a width of 2, or it looks like this. Doesn't it, class? How many see this? Now that's a simple reasoning process to come about that answer, but that's what's going to be expected of everybody here to do that. You're going to be able to reason your way for any of these crazy functions and show and draw them and understand them. Understand, class? Out of curiosity, this is a little tougher. I didn't cover this yet. What would this function look like? I want you to think about this. Let me put a 2 down here and put 2t, not t. Think about it. What does that look like? Well, first of all, where is it centered? When the argument, or it's centered at 0, right? Now, think about it. The width is 2, right? It can go up 2 and down 2, correct? Now, this is the thing that's a little, the rect function might be a little better at this because it actually includes here. It includes the tau right there. So let me use this, the rect function for this. I know it has a width of 2, right? So if I put a rect here of t over 2, right? And I looked at it, I know that t minus 2, the width is 2. I'm sorry. Wait 1 second. I got to do something. You're right about that. I'm going to take the rect here. First, let me just put the function. It was originally t over 2, correct? That was the original. Now I'm going to multiply it by 2 because then it'll make sense to you. This was the original that was the thing that I had up there. Well, I mean, I would have up there with a width of 2. But now when I multiply it by 2, what do you see happening? They cancel, so the width of this function is 1. It's easier with the rect function. How many see this right here? All right? Got it, everyone? Do you see it? Yeah. Okay. Whenever I get somebody looking like, I'm worried that I didn't get through. So this has a width of 1. It's still centered at 0, so it goes down to 1/2, minus 1/2, and up to 1/2, and it's simply like this. Follow me? I guess the rect function is better for some of them, but I always like the pulse. Yes?
Can you kind of explain how you do that again?
Sure. Let me first, I'm going to go right to this function, right here. The pulse function p tau of t is the same thing as the rect function, R-E-C-T, t over tau. The width right here is always going to be tau, but that tau is always going to be what the t is over, the rect function. All right? Now, it's not shown here, it's implied. That is a shorthand version, I guess. This is what you use most of the time. So if I have this, and now I say that I have an original function, let me just draw it up here. If I have rect of t over 2, this function is centered at 0. T over 2 would be 0, t would be 0, right? and it's got a width of 2, which would mean that function starts at -1 and would end at 1. This is the way this function would look, right? You follow me on that? All right, now, what happens if I do a multiplier of 2 in here, or 2 here? Well, if I put 2 here, you see those 2 cancel, and now I have rect of t, right? What is it t divided by? It's implied 1, isn't it, class? If it's divided by 1, that's the total width from -1/2 to +1/2. Follow me on this? How many see that? I hope I help you get that one. Okay. You were looking through my back too, I understand. Sorry. Are you with me, class? All right. Anyway, that's a rect function. Last function I'm going to cover before you do some problems is something called a triangle function. He doesn't use the symbol I use, but I like the symbol I use, and it's easier, so I'm going to show you. As you might guess, it's going to be something that looks like a triangle. And the symbol I use is this. It's the triangle function. This tau is the width. Follow me, class? It's defined, mathematically, it's defined as this. It's just equal to 1 minus the magnitude of 2t over tau times a pulse function of t. You can put a rect function there too if you want. This argument is t. Are you with me? Now, let me just show you what it looks like. It looks like this. It's a triangle. That's all it is. It starts at -τ/2, it stops at τ/2, goes up, it's a peak, goes down. Mathematically, let's take a look at it. When t is 0, what do we have? We have 1 times p tau of t. If it's 0, it's 1. Now take it all the way up where t right here is τ/2. τ/2, right? τ/2 times 2 is tau. Tau divided by tau is 1. 1 minus 1 is 0. Goes to 0. Follow me on this, class? And the same way on the other side. That absolute value gets rid of the problem with the negative values for t. Y'all see that, guys? Everybody? All right, now that's a triangle function. He actually writes this thing out like this. And I don't like that. I just use this. That way it's implied, it's clear. Most books, well, the Pi book use this. And it's very easy to understand and learn from. Okay? Yes, sir.
What's that in a number rate?
Oh boy, I'm sorry. You want to move up front? Seriously, if you have problems seeing it, I'll try to write bigger, but I'm trying to get anybody. I hope that isn't a bomb. No, I was teaching one time. That's really a countdown for that camera to go if I think of something. And as I recall, all the lights shut off. They don't do that. This system has been inactive. Shut down. Doesn't take a hint, does it? All right. Look, I don't know what's going on. What do you want me to do? This. Or stay tuned. Sorry about it. All right, now the next thing we're going to do is try to actually describe. There's two things you do: is describe functions with known functions, or describe plots with known functions, or plot things based on known functions. So far, we've been just plotting based on known functions, right? Let's try this. How would you describe this function I'm going to put up using just u of t functions? Now, I think you'll get this one. It's fairly easy. So for this one, this is my x of t here versus t. That's 0, 1, 2, 3, 4. And I want you to show me how to describe this function. with just U of t functions, how would you describe this? Most of you are clever enough to get this in RP. You don't want to show off though. I'm just looking for some discussion. I'm trying to prod you people into saying something in class. So it's 0 until when? So how about we say x of t equals u of t minus 1. At least it turns on there, right? Keep working with me here. Now it stays 1 until when? And what happens? All right, so what do we do now? Minus for sure, right? Minus what? 2 u of t minus 2. Keep going. Stays at minus 1. It's minus 1 now, right? Right? Keeps it minus 1. And then? Very good. Plus u of t minus 3. You all see what I did there? It's a very straightforward thing, right? Not too many steps at once. All right? Now, what if I asked you to take this? Well, I'm almost afraid to go down this too far. I can do things where all of a sudden now, what I'm going to say, with this functional form, your x of t here, go ahead and graph x of minus t plus 7, something like that. Are you with me? Then I'm going to ask you to take this expression and then have, instead of the argument t right here, have it minus t plus 7 or minus 7. Are you with me? Then that's the kind of problems that really force you to think and really sort of in an abstract way. You've got to visualize things and reason through them. And they're very challenging, some of them. I'm going to give you some of these. I'll tell you for next time, because I'm about out of time, I'm going to be talking about convolution. And I'm also going to talk a bit about using, all these functions we looked at are analog functions. We're going to get into discrete functions, all right, where we have, well, I'll get to it later. They're all the same symbols. It just has slightly different meaning. Yes, sir.
I'm just confused on where the.
What's that?
I'm just confused on where the 2 comes
Okay.
from.
I'll answer that in a second. Listen, folks, could you do me one favor? Get a book by next class period. All right. All right. That's Friday. I'm not going to give you a quiz this Friday. I'll get 100 emails. Everybody will be saying, "Is there a quiz?" No, not this Friday. Get a book, all right? And this Friday, what I'm going to do is take you through, in my opinion, the most difficult concept you'll be facing this entire year, and definitely in this class. It's called convolution. Yeah.
Is the name of the book on the syllabus?
Yeah. Isn't the book on the syllabus, guys?
Yes.
It should be in the bookstore. Just go over there. Okay. You have questions?